So if I'm doing a dot product with itself, the angle between them is 0. And so cosine of 0 is 1. So it just becomes the magnitude times the magnitude. Other questions?
How many more tests do we have left?
2 officially. There's the multiple choice test, and then there's one more calculator test, and then there's that multiple choice test.
The one you already gave us.
Yeah. We'll see it again.
Wait, is that just test 3 then?
Yeah.
I don't know what we took in the beginning of the class.
Yeah.
Oh, what, was it a grade when we first took it?
No,
Oh,
that was just see where you are.
oh.
It'll be great the second time because we've covered the material.
And I wish I was like memorized those problems.
If anybody remembers them, feel free to talk amongst yourselves about it. But
So is that the next test coming, or is that like the final?
typically the final, the last day test is the calculator chapters 8 through 50 or whatever.
Oh, so that's like our next test, really? or-
Yeah, the next test grade will be that multiple choice.
Okay.
Since all of you know this stuff so well, 15 minutes, everyone's done.
Oh,
Yeah, man.
You know it well, and you've taken speed reading.
wishful thinking.
There was a question, Will, was that?
Do you, if that was to turn in the test corrections, would I have to turn in the test?
I would prefer that, yes.
Okay.
Wait, so with, how many more like chances do we have for test corrections? Like, will there be test
Test
correct?
1A and 1B. Those
Okay.
are the ones that you get test corrections on.
Okay.
Do you want them stapled together?
The test and the test corrections?
No, keep them separate, is fine. Excuse me, Will, there's a stack already.
I thought that was for something else.
No. Would be inappropriate for me to say who raised you, but. The wolves, was raised by wolves. Other questions? All right. Sort of summarize some of the things that are going on here. We basically first started looking at the physics from the point of view of force. We've now gone into looking at it from energy, and we're about to launch into momentum. If there is a change in linear motion, let's be more specific, linear velocity, then that means that there is some external force, a net external force acting on the object. Newton's third law, or sorry, Newton's second law, F equals ma. If there is a change here, then there must be work being done. If there's a change in the momentum, if there's change in velocity, then there is impulse. Mathematically, this would be equal to ma. This is going to be equal to, depends on what type of work. If it's total, this is change in kinetic energy. If it's conservative work, negative change in potential energy, and non-conservative work, change in the total energy. And then impulse, change in momentum. Now, work has force built into it. The work, as we've talked about today and in the past, is F dot dx or dr, whatever you're using. Impulse also has force built into it, F dt. And that is the vector quantity. And then we can also talk about the rotational velocity or angular velocity. Rotational and angular can be used interchangeably. Typically, rotational motion, angular velocity, but talking about torque here. And that is equal to I alpha. If you have not had physics, you might be looking at that I and thinking, is that impulse? No, it is not. This I is a scalar, this I is a vector. This I right here is not the magnitude of this.
Is that change in P?
Yes,
What does P represent?
moment. Work is the integral of, if we're talking about work from rotational motion or rotational influences, that'd be torque dot d theta. All I did was I take the linear components over there and I just write down the rotational equivalent, or sorry, not equivalent, but analog, probably better wording. And impulse, or rotational impulse, that's probably not the best color there. Yeah. That's an R. Rotational impulse is equal to the change in angular momentum. Which would be equal to the integral of tau dt. Tau torque. So to sort of give some perspective, the one other type of motion that we deal with in this course, we've got the linear motion, rotational motion, and then there's harmonic motion. Which is like, it's linear motion, except if it's moving in harmonic motion, then there is definitely a force acting on it.
What's the line above the alpha for rotational?
That's a vector symbol.
Okay, gotcha.
Is that DH next to torque?
Here,
Yes.
dt.
Oh, DT.
And is the alpha the angle?
No. Angular acceleration.
Okay.
Alpha.
Theta is the angle. This is angular acceleration.
And you said there was a difference between the I on the left side and I on the right side?
Yeah, this I right here, the scalar, the vector symbol over it, this is moment of inertia.
Okay.
If you get into mechanical engineering or physics as a major at the four-year school, then you'll realize that we're talking about moments of, there's this whole range of formulas dealing with moments, and this is just one of them. It's like the second moment of area or something like that. I forget what the other official name for this is, but in physics we call it moment of inertia, and then it gets more complicated the more you get into it. We will not get past this moment of inertia.
And the other I with the vector symbol was the impulse?
Yes.
Okay.
Just like the perfume ad in the 70s, which I'm sure all of you remember.
Would you be disappointed if I said I did?
It typically is my most obscure clue that I ever drop. It's when someone suddenly buys you flowers, that's called. and then people come up with crap like, it'd be nice, some stuff like that, but it's impulse.
That was like 50 years ago.
Yeah, I'm old. Alright. So we talked about work, people have asked questions, but let's talk about momentum, and then I'm hoping we'll get into the rotational motion. And actually try to get into what I is. Now, there is a video where I did the derivative. I am going to do the derivative again. And because there are a couple points that I want to emphasize because they are that important. We were starting with the premise that F equals ma. Actually, we're going to start with the premise that Newton's second and third law are both valid. So if I have two objects, the force on A from B, it's going to be equal to the negative force on B from A, Newton's third law. Let's combine these, that the force on A would be the mass of A times the acceleration of A is equal to the negative mass of B times the acceleration of B. Now, when two objects interact, yeah, we have a whole, 151 is dealing with the fact that, hey, let's pretend the force is constant. But we don't have to, because we're more sophisticated mathematically. Yes, yes, you are. So what I'm going to do is that, because the force can change with time, let's go ahead and multiply both of these by some infinitesimally small change in time. So that's mass of A times the acceleration of A dt is equal to the negative mass of B times the acceleration of B dt. Because remember that we talked about that when two objects interact, they interact with each other for the same amount of time. A influences B for the exact same amount of time that B influences A. And because we have a differential here, we can inverse. Now, as we integrate here, well, what is acceleration anyway? Mathematical definition.
Just, it's the derivative of velocity in respect to time.
There we go.
Oh.
So we have mass. We'll assume for right now that the mass is a constant. We'll pull that out. So I'm left with the change in velocity of A dt is equal to the negative mass of B times the integral of dvb dt. dt is canceled. And so I change my differential into dv from some initial velocity to some final velocity. V initial B, V final B. That's VA. And the integral of dv.
One. Sorry, X or whatever variable you're using, so, V.
So this becomes the mass of A, VA from VI, A to V final, okay? Negative mass of B, VV from VIV to VFV. Continue with the integration, so we got MAVFA minus VIA. These are still vectors. Distribute, get mass of A, VFA, plus mass of A, VIA, equals negative mass of B, V final B, oops, there should be a minus there, plus mass of B, V initial B. We're gonna take this one more step. I'm gonna get all the initial stuff on one side and all the final stuff on another. So I'm gonna take the initial stuff over to the right-hand side, the final stuff over to the left-hand side. In other words, bringing this term over here and this term over here. So I have MA, V final A, plus MB, V final B, equals VA, V initial A, oops, sorry. MA, V initial A, plus MB, V initial B. This kind of equation makes physicists' hearts go all aflutter and a twitter. Recognize the implication here. We have this mass times velocity, and this on the left-hand or right-hand side, as you kids today say, this on the right-hand side is the total of this mass times velocity before the interaction happens. This is the total afterwards. Whatever I started with, I end with. This is in physics known as a conservation rule. And mass times velocity, they don't feel like calling it mass times velocity. They wanted to give it a single word name, and that is momentum. So this is the conservation of momentum. Where momentum is equal to this P, which is just mass times velocity. So we can summarize this. P initial is equals P final.
That means, is momentum always conservative?
Always conserved. It's not a conservative, momentum is not conservative, it is conserved.
Okay, so that's always a constant, like P initial is always equal P final?
All right, so let's talk about that. When is it not? What is the assumption that I made here in the beginning besides Newton's laws were true?
That the force was constant?
Now, force is not necessarily constant, that's why I did the integral.
The mass is constant?
I did make that assumption. Mass actually does not have to be constant, as it turns out. That's when you get into the rocket problems, which we will skate by very fast. Just, if you get into aerospace engineering, you will get that stuff. It's more than you ever dreamed of. How many objects are involved here?
2.
The assumption is I've taken all that into account. I've taken into account any interaction that's gonna happen. So, in other words, there's not a third object influencing them. So momentum is conserved if it is a closed system. which I think formally is that there's no external force. Practically, it is, we've taken into account anything that is actually changing. Any influence, we're taking that into account. This has a very distinct advantage over conservation of energy in the fact that we don't lose direction. Vectors, these are vector quantities. It has the distinct disadvantage in the fact that we have to take direction into account. There are times in which conservation of momentum is really convenient, and times when conservation of energy is really convenient, and times when you just have to go back to the classics, Newton's laws. And I will tell you this. Momentum being conserved is really convenient if there's a collision. Then we will pretend it's a closed system. And I will tell you, on the last test, there will be at least 2 collision problems on the last test. One where they stick together, and one where kinetic energy is conserved.
Can we go over a problem with that? Just to like.
What the heck? Let's do it. Every time I teach 151 and 251, I tell them there'll be this type problem on the test. And I'm thinking, great, because when I get to the test, everyone will get that right. It's shocking how few people get it right. And there was one test, pretty sure it was a 251 test, where I asked them to figure out what is the total initial momentum. There's a collision happening, what's the total initial momentum? Next question, what's the final total momentum? If you know the initial, I hope you know the final.
Because what I think about it is like, I don't know, if you slid an ice block across the floor, it starts at a stop and it has to end at a stop, or else like there's something wrong with it.
If you're sliding it, if it starts at rest and it starts sliding, then you're introducing there's another force involved.
Yeah.
If it's stopping, well, is it stopping because of friction? Then there's another force involved.